Hello, Honors Chemistry, and welcome to Chapter 3, where we talk about matter and energy. In Chapter 2, we set the foundation for the math, the type of math that we will do all year, right? Dimensional analysis, understanding the relationships between units, and we introduce the concept of matter, right? As in matter is synonymous with chemicals, right? Where both of those, right, at their core are things that are made up of atoms, which is almost everything in the world, right? And now we talk a little bit more specifically about states of matter, types of matter, changes that matter can undergo, right? Which is where the energy comes in, because most changes have energy associated with them. All right, so for starters, we have our states of matter here, okay? This is really, really important, right? Because states are different than type of matter, all right? So you need to be thoughtful about that. When we talk about states of matter, we're talking about solids, liquids, and gases, and we're talking very specifically about the space between the particles. That's all state of matter refers to, right? In a solid, my particles are closely packed and they are fixed and rigid in orientation, right? The way that all of those are arranged in the same way, right, in a very specific way, orientation specific, based on the types of attractions between the particles, right? And for most substances, water being the rare exception, right, the solid state is the, the most dense phase, right, because all the atoms or molecules are squished as closely as possible in 1 unit of volume, right? Whereas in a gas, my particles are so far apart, right, and there's so much space between them at that point, right, that for the most part, we can't even perceive it as a solid, right? When we put our hand through, for example, when we're trying to waft scents away, for example, which are just, gaseous molecules, right? Because there's so much space between the particles at that point, right, that our hand can't even pick up that feeling, right? And liquids are obviously somewhere in between, right, where they have properties of both of them to some extent, right? They are much, much closer to one another, such that they do have properties like defined volumes, right? But they are not, and they flow past one another, which is like how gas particles do, right? But they are fixed in volume. Note that technically both of these would be considered fluids, in that in both of those, the particles are able to flow past one another, right? All right, so states of matter, distance between particles, not to be confused with types of matter. So type of matter has to do with the types of particles that make up that particular substance, right? So for example, elements are made up of atoms, right? Only atoms, right? Because elements are made up of only one type of atom by definition, right? Compounds are made up of molecules, right? Where molecules are atoms that are chemically bonded together, right? But the thing about a compound is, even though there are multiple types of atoms, right, those atoms are chemically bonded in such a way that we still have only one type of molecule, right? One type of molecule makes up that entire sample. Like, so for example, when we look at a sugar cube, right, every single particle of that sugar cube is the exact same as the neighboring particle. Yes? Makes sense? Okay. Which then brings us to mixtures, which are unique and different in that whole concept of one type of particle is no longer relevant, right? So for example, if we look at a homogeneous mixture, all that means is my two types of particles are evenly and uniformly distributed, right? So here we have water molecules, and we have all the different compounds that make up tea, right? And we have our sugar molecules, and these molecules all hanging out together, evenly distributed throughout the solution, right? Homogeneous mixtures are often solutions. And all of those are evenly distributed, right? So note we have so in the picture view that they give you, right? We have 3 different types of molecules, all evenly distributed throughout, okay? Homogeneous mixture could well be different types of atoms. I guess there are certain types of metal alloys where we would have atoms that are evenly distributed. Heterogeneous mixtures means we have different types of molecules, right? That do not intermingle in a uniform way, right? Thus heterogeneous versus homogeneous, right? So we have one type of molecule up here, one type of molecule down here, and they don't intermingle, okay? which goes back to their type, their respective properties, which, like you guys talked about in biology, some molecules are polar, some molecules are nonpolar, and that's what determines whether or not they are able to interact with one another, okay? So then, if we were going to identify certain types of matter, right, clearly, this is an example of, right, an element, right, because there is only one type of particle, right? And then, for example, here, this one is clearly a, right, this one is clearly a compound because we have multiple atoms, but all those atoms are chemically bonded together such that there is still only one type of molecule that makes up that whole compound, right? Here we have a mixture of molecules that seem to be evenly distributed amongst each other, right? Which means that that would be our homogeneous mixture. And then down here we have that exact same array we saw with the oil and the water, right? Where this would be our heterogeneous mixture. Yes? All right. Moving along. So obviously our different types of matter, right, can undergo, well, they have physical and chemical properties, right, which you should have jotted down from your reading. And those physical and chemical properties, right, can undergo physical and chemical changes. But that goes back to our states, right? So our physical changes are going to be about states of matter for the most part, right? Physical changes are typically going to involve changes of state, right? So here in this example, right, we have liquid butane down here, which turns into gaseous butane once we, and so this would be if we push down here without clicking this part, okay? So we don't use that, and we only push down here, right? Then all that does is basically open this hole here so that it can escape, and we get gaseous butane, right? So that's when you can like hear it coming out of the lighter. Or like a propane tank on a grill, for example, that would be a good example, right? Or here, right, where we have heat being applied to a, what is that called? A pot of water, right? And it's turning into steam. So all we're doing is adding enough heat to separate my molecules one from another, put more space between them, but those molecules remain unchanged, yes? That is the basic definition of a physical change, right? The particles, right, whatever they are, be they atoms or molecules, are unchanged from before to after, yes? Whereas in a chemical change, by definition, the molecules or atoms, right, have been rearranged, right? Bonds have been broken, new bonds have been formed, such that we have new molecules or atoms on the product side. So here, we have our liquid butane again, but this would be like if we strike down this whole thing, right? So we have to turn this part because that's where the sparks come from, right? So now we have a spark as we release our liquid butane and turn it into gaseous butane, right? And we get this fire, right? This lovely fire, which then makes carbon dioxide and water vapor, right? Which means that we no longer have butane, right? Bonds have been broken, new bonds have been formed, new molecules, right? Likewise here, right, we start off with something that is an element, and we expose it to enough water and air, right? And then it reacts with that oxygen eventually and forms iron oxide or rust, right? Which is new chemical bonds being formed, right? So now instead of iron being bonded to neighboring iron atoms, now those iron atoms are bonded to oxygens, right? New chemical bonds formed, right? And it is no longer what it was before. Yes? Key difference. All right. Now, important to note, right, that when we're talking about something that is a pure substance, right, so either this or this, right, so this, obviously an element cannot be separated into any smaller parts, right, that's the definition of an element. A molecule, though, right, would have to undergo some type of chemical reaction to break apart the atoms that make it up. The thing that sets mixtures apart is that because all the molecules are unchanged, right, like this is just a collection of different molecules, this is a collection of different molecules, they all retain their own individual properties. Because they retain their own individual properties, we can separate them, taking advantage of those properties, right? So one of the simplest methods would be, like in your book, decanting, right? Where what is decanting? Right, it's just a fancy word for pouring off one layer, right? So thinking back to that oil and water, right, we can simply tip this cup over, right, and some of that oil would pour out, right, and we would have separated them. It's not a very good separation, so it depends on what the goal of my separation is, but that is the simplest thing to do, right? Note that decanting is only useful, right, when we have either two immiscible liquids, like oil and water, Or if we had a heterogeneous mixture of a solid and a liquid, then we could pour the liquid component off of the solid, right? Filtration only works with a solid and liquid mixture, where we have filter paper here, right? So my solid is always going to get caught on my filter paper, right? And the liquid is going to flow through and get caught down here. This liquid component, by the way, is known as the filtrate. One of those terminology things I think you ought to know. And it looks, so if you have one of those old school drip coffee makers at home, this is that same exact process, right? Where our paper is where a solid sits and the liquid flows through, right? The last one, which does require some special setup and equipment, is distillation, right? Where in here, this is typically for two miscible liquids, right? More often than not, distillation is used for two miscible liquids. And what we do, right, is we take advantage of the fact that each liquid retains its own boiling point, right? Each liquid retains its own boiling point. So when we have this mixture of liquids, and we add this heat, right? The liquid that is most volatile, in other words, the one that has the lowest boiling point, right, will start to boil first, right? And as it boils, right, physical change, meaning that it becomes gaseous. That gas is able to travel up here, then down through the condenser, and just like the name states, right, that is where my gas condenses back into a liquid, because here we have a part in the middle where your gas goes, right? And then we have an outside area where cold water flows, right? And as the cold water is basically surrounding my gas, that gas condenses and drips back into a separate flask. And now our more volatile liquid collects in there, right? And in real life, right? Like, so if you do this lab in college, right? You would have a thermometer here to help you keep track, right? And as that first fraction is boiling, right? That thermometer should register the boiling point of that first liquid, right? And once all of that liquid has boiled off, the temperature will then start to increase again to signify that now we are reaching that second fraction. All right, finally, law of conservation of mass. I know you talk about this in middle school, so we're not going to talk about it much. But obviously, what does this say? Right, that mass is neither created nor destroyed, right? What that means is atoms are neither created nor destroyed, because those are the particles that make up everything that has mass, right? So what that means is however many atoms we start with, we have to end with that much, which means that however many grams total we start with, even though we are rearranging the bonds between my atoms, right? And we have whatever we form on the product side has vastly different characteristics and properties, the fact remains that the same total amount of substance must exist, right? Which is one of the most amazing, awesome things, right? That all the matter there is the matter that ever was, right? So anyway, just cool life things. All right. This is the end of 3.7, so we're going to stop this video here. Thank you for listening. Be good and stay tuned for a little bit of math in the next one. All right. Thanks for listening. Be good, and I'll see you soon. Bye.